So in this video, I want to talk a little bit about CPU scheduling and the various sorts of algorithms that a CPU scheduler can take on. First thing I just want you guys to know, just some quick facts about the CPU. The CPU is preemptive, meaning that it can be taken away from a certain process. We can't do that with memory. So if you have a process running and it's executing in some sort of virtual addresses, you can't just take the addresses or take that memory that has been allocated in the middle of that process running. CPU is a bit different. We can take away the CPU from a process and give it to another process. We're going to be ranking each of these algorithms based on 6 different criteria. So latency, throughput, overhead, fairness, strategy proof, and predictability. And throughout the video, you'll see what those kind of mean. And each of them will have advantages and disadvantages for the different types of scheduling algorithms. So the first one you probably are very familiar with in your data structures classes. You have a simple FIFO queue, and a FIFO queue is whatever jobs, we're going to call them jobs in replacement for processes. So processes are just having some sort of instruction that they want to have executed. We'll just call those jobs. These jobs enter a FIFO queue, and the CPU will one by one pluck each of these jobs from the queue and execute them in their entirety. So this can be a bit problematic because if you have a long running job that's at the very start of the queue, well, the CPU is going to spend a lot of time executing that job in total, like all of it. It's going to try to execute all of that job before it moves on to the next job. And so that can cause a lot of backlog if there is a long running job in the beginning of the queue, but there's a lot of short running jobs right after it. And so you can see that the latency is very high and the throughput is very low, meaning we're not getting as much jobs completed in that queue. And but the overhead is pretty good. You have a low overhead, and it's not, some may say it's not very fair, but some may say it is fair in the fact that if it's first come first serve, if you feel like that's a fair criteria. But if you're judging in terms of giving the CPU to everyone, all the jobs, it's not very fair. And then you have strategy proof, meaning that you can have a program just queue up it can queue up a job that takes a really long time, and it blocks all the other jobs behind it. So in that way, you can kind of manipulate the scheduler to get your task finished with and stall everyone else behind you. Then you have shortest job first queue, which is just a queue that we're going to prioritize jobs that take very less time. So this kind of solves that problem of, hey, if there's a large running task in the beginning of the queue, we're just going to neglect that and run all the short jobs first, and then we're going to come back to it. However, you may see that is problematic as well, because let's say you have a lot of short jobs running, and then you keep having short jobs coming into the queue. Those long jobs are going to be starved, and these long jobs are just these are just programs essentially. These are going to be starved, and they're not going to get any CPU time at all. So you can see like the latency, throughput, and overhead does increase a little bit, or does get better a little bit, but it's not very fair to longer tasks, and it's not very strategic proof, meaning that we can manipulate this scheduling algorithm if we just keep inserting short tasks. So how that would work is, let's say I'm a program, I have a very long task that I need to execute. Rather than inserting the entire long task in the queue, I'll just break it up into little bits and just insert those instructions into the queue for the CPU to run. And that way, my CPU will consistently run my short instructions over and over again, and I'll block everyone else behind me. So no one else will be able to basically get their instructions ran by the CPU, because I'm consistently giving the CPU short instructions, and it's going to prioritize that because they take less time. And then you have round robin queues. So round robin queues are going to solve that problem of, hey, we have a lot of items in our queue, but we're prioritizing all the short ones and we're starving on the long ones. Well, why don't we just become pretty fair to everyone and just give everyone an equal time slice out there, where we call this time slice the time quantum. And this time quantum is just going to determine how much time a CPU is going to spend at a specific job, or how much it's going to run a specific job before it switches to the next one. Now, if you know stuff about context switching, this can cause a lot of overhead, because let's say we have a queue filled with a lot of tasks of the same size. When I say size, I mean they take relatively same amount of time to execute. Well, if we have a CPU that's switching between each of these tasks, let's say every 1 second or so, the CPU has to offload its registers and then onload all the registers of the next process that's going to run. This causes a lot of context switching overhead. So it's not really good in that sense. In the sense that it is strategic proof, because it's a time you can't really game the system here. Like a process can't do anything to get ahead, right? It just every 20 seconds or 10 seconds or whatever seconds that the OS sets, it's just gonna give each process the same amount of time switching, execution time. And the latency is pretty high as well, because you have many long running jobs of equal size, and the CPU may switch. So that means a task can't really complete in its entirety. So the time that it takes for a single process or a single job to execute is very long. And then second to last is multi-level feedback queues. So these are like kind of branching on top of the round robin queues, where we have multiple round robin queues, each having a different priority out there. The very first round robin queue, or the very first priority queue, is just going to be, the very first round robin queue is going to have the highest priority, meaning that this is going to have a small time slice. And these small time slices are really meant for short running tasks. So if you're a short running task, you can just enter into that queue and you'll be executed. But if, let's say, you're a long running task, by default you enter into the highest priority queue, which is the one with the lowest time slice. If, let's say, your execution time is not done, or your job does not complete before the time slice expires, meaning, let's say it takes 10 seconds for your job to run, but it's a time slice of 1 second in the highest priority queue, well, then you're going to get demoted to the next queue because your time slice expired. You're not a short job, right? So you're a longer job, so you're going to go down in priority. And this keeps happening. And these jobs can keep going down the priority queue. You may be wondering, well, doesn't this lead to starvation if, let's say, all the short tasks are getting executed first by the CPU and leaving all the bottom ones left alone? Well, if the OS recognizes that a job is being starved, meaning the CPU is not getting to run that process, it will bump that job up in the priority queue. Or it will bump that job up a priority queue, meaning it will have more priority. So let's say you had like 7 priority queues. Let's say it was at the 7th one, it'll move to the 6th one. And then maybe a little bit after, it'll move to the 5th one if it's still getting starved. Then you have fairness queues, and fairness queues are probably the most optimal in my opinion, where we are going to be pretty fair in the sense that we're going to give all jobs, let's say we have 4 jobs in our queue, we're going to give them all equal CPU time. Now, you may make a connection, like this kind of sounds similar to round robin. Well, in the sense of round robin, the difference here is that, let's say I'm a short running task, I have 25% of the CPU time, meaning the CPU is spending 25% of its time executing me. If I don't need all of that CPU time, I can just give up, and I complete before the CPU time switches. I can just give up the allocated time that was allocated to me that I didn't use. Okay, so for example, let's say you had 4 jobs, each of them have 25% of the CPU. I finish early. Well, now the CPU will spend 33% on each of the 3 remaining jobs, right? So in that way, we're dynamically allocating CPU time, and the splits are more dynamic. And so in that way, you kind of get the most optimal low latency, high throughput, low to moderate overhead, because there's not too much switching going on. It can depend on if, let's say, you have more. It depends on how your time, how much time is being dynamically distributed to jobs after to the remaining jobs that are still trying to complete. But it is fair in the sense that each task is getting proportional amount of CPU time, and a user can't really game this system, or can't really do anything to get more CPU time. The trade-off is that it isn't predictable. And this is kind of good in a way, because you don't really want a program to know how the scheduler works, because they might take advantage of it. And so because it's not predictable in the sense that you don't know how much time or CPU time is allocated. Like a program doesn't know how much CPU time is allocated to it, nor does it know how many other programs are running concurrently with it. So that was a quick overview of CPU schedulers. Feel free to just look into the slides as well. I didn't go too deep into what the slides were, so if you want to read over the slides, go ahead, but hope you guys enjoyed.